So in addition to using the integrated rate law, sometimes what we do is we can describe the rate of the reaction. We can describe a reaction rate using what's known as the half-life. That's a term that you may have heard about before, but we need to define that in terms of what it means technically. The half-life itself is often abbreviated as T, lowercase t, subscript 1/2. And what the half-life is, it's a measure of time, right? So it's a time needed, or the time required for a sample or reactant, in other words, reactant sample to decrease to half of its original, whatever that original value actually is. All right, so that's how we define the half-life of something. It's the time needed for the reaction, for the reactant to drop to half of its original value. So for example, let's say at time equals 0, the reactant, let's say the concentration of something was 0.50 molar, and then the time that it takes for that to become 0.25 molar, right? That time there would be your half-life, whatever that happens to be, 5 seconds, 10 seconds, an hour, millions of years. That's what the half-life actually is, right? So if we can write now the expression for the half-life, right? So if we have T, if we have our T in our original integrated rate law equation over here, if I want to isolate just T on one side because I want the half-life. If I divide this side by K, right, I need to divide this other side by K as well. So I end up with 1 over K times natural log of A T over A0, and that is going to be equal to negative T. Right, if I multiply this side by -1, I need to multiply this side by -1 as well, but I get rid of the negative sign. Okay, and the way that this works, right, is I'm going to have 1 over K times natural log of A now 0 at time equals 0 over A at time t, right? So when you have that negative sign in front of the logarithm, you essentially flip the relationship over on this side. If I define the definition of half-life, right? So according to what we mentioned over here, right? When so T is equal to T 1/2 when the concentration of A times T is equal to half the concentration of A at time 0, right? That's how we define the half-life. So the time that it takes for the concentration to become half of the original. So if I substitute these now back into my rearranged equation, right, what I end up with then is T 1/2, the half-life would be equal to 1 over K times the natural log of A0 over half of A0. Okay, and because this expression here, 1 over 2 is the same as 2. So this becomes 1 over K, natural log of, this simplifies to 2, is equal to T 1/2. Right, we evaluate the natural log of 2. What is, stick that in your calculator, you get 0.693 is equal to T 1/2, and then that times 1 over K is the same as 0.693. Okay, so what we've done is we just went ahead and we've derived the expression for the half-life for a first order equation. So the T 1/2 is 0.693 over the rate constant K. So we can use that also to solve different chemical/mathematical problems. one important implication of this this equation for the half-life, right, is that the half-life is independent of the initial concentration, right? So T1 half is independent of the initial concentration of the reactant. So the time that it takes for, let's say we had 1 molar of something to decrease to 0.5 molar of that thing, right? So that's the time, that would be the half-life, is the same time that it would take if I had 50 molar of it to decrease 25 molar of it. It's the same time, right? The half-life is the same because it is independent of the starting concentration. It's just the time that it takes for that starting concentration to become half of what it originally was. So another thing to note about the half-life is that it is inversely proportional to the rate constant K. And what that means is we can make some qualitative relationships. So half-life is inversely proportional to the rate constant K. What that means is as K increases, T1 half, the half-life decreases, and then vice versa. So as the rate constant decreases, the half-life increases, right? That's the inverse. One goes up, the other one goes down. So what that means is a short half-life, small half-life, if you will, corresponds to a large rate constant. And similarly, a long half-life corresponds to a small rate constant. Right. So again, I mentioned that you may have heard about half-lives before. A lot of times half-life itself, we see it in terms of like, radioactive substances. So, in nuclear power plants, for example, the reason why that those waste products have to be buried deep in the earth is because they have super long half-lives, right? It takes a long time for that waste product to degrade to half of what it originally was. We often have half-lives associated, for example, with medications that you take, right? So you take a medication, how long does it take for it to decrease to half of its original value? Well, those tend to have shorter half-lives, right? No, not on the order of millions of years, but sometimes on the order of minutes or hours or even seconds in some cases. So those are some instances where you would see or you would associate the idea of half-life with regular everyday occurrences. So take a look at a very simple example of this. So we're told here the decomposition of ethane to methyl radicals is first order. So that's the first thing. And then we're given the rate constant of 5.36 times 10 to the negative 4 per second at 700 degrees Celsius. This is a this is not a completely correct equation. Let me rewrite this. This is the same equation we saw previously. We get 2 of the methyl radicals over here. So it's first order with respect to the reactant. So we can write the rate here, equal to K times the concentration of C2H6. This is something we saw previously. We're told that the rate constant K is equal to 5.36 times 10 to the negative 4 per second. What we need to find is the half-life. So we need T1 half. Okay, and as we saw previously, we can use the equation T1 half is equal to 0.693 over the rate constant. And we can just simply plug this value in. So we have T1 half equals 0.693. And then the rate constant there is, what is that? 5.36 times 10 to the negative 4 per second. All right, so we're going to get our answer here in seconds. we want the rate, we want the half-life in minutes. So don't forget, this is often a simple thing to forget to do. Make sure you do the conversion. So we end up with seconds, you want to convert it to minutes, you divide by 50 seconds, you end up with about 21.5 minutes per hour. All right, so it's compared to some of the equations we saw previously, it's a lot simpler, fewer steps involved, but we do need to know what that relationship, what that expression for the half-life is for a first order reaction.